Okay, so let's have our class. So this will be our last class. We started this topic last week, semiconductors, which are materials that have properties between insulator and a conductor. So we mentioned the types of semiconductors we have, which are intrinsic and semiconductor. And we explain what intrinsic semiconductor is and the extrinsic semiconductor. Last week, we did all that. And how N-type semiconductor is formed and how P-type semiconductor is formed. We treated all this last week. And we talked about majority and minority charge carriers. Now, in semiconductor, we know that there are two charge carriers, which are electrons and holes. So either of them could be a minority or a majority charge carrier. It depends on the semiconductor material. So for instance, in N-type semiconductor material, since we have free electrons, majority carriers are electrons, while minority carriers are holes. And in P-type semiconductor, there are no free electrons as such. Holes outnumber the free electrons. Therefore, majority carriers are holes, while minority carriers are electrons. And then we talked about electron mobility last week. And I gave this formula. I said E instead of Q. I prefer E, where E is electron charge, which is a constant. So you can call it, I don't want it this way, never. Give it an acronym of never. So I is never. N for number of electrons. E for electron charge, which is a constant value, 1.6 times 10 raised to minus 19 coulomb. V for the drift velocity, and A for cross-sectional area of the material. So here we have an example. Say the area is given, the cross-sectional.
Well, when are you going? I'll give you my card.
Current
Go
is
to the
given.
market now. To go and buy watermelon, carrots, chicken is at not those places.
My bro, off your mic with the class.
So with that never formula, should be able to calculate, find the drift velocity. The drift velocity, we are asked to find drift velocity. So current is known, which is 3 ampere. Area is known, which is 1 millimeter square. The number of electrons is known, which is 8.5 times 10 raised to 28 per meter cube. And then electron charge, E, is a constant. We are asked to find V, drift velocity. So by the time you substitute all those parameters and make V the subject of the formula, you get your answer as 2.2 meter per second. And we also talked about relationship between drift velocity and current density. Current density is J. We first come across current density under Richardson-Dutchman equation. So current density is directly proportional to the current. J is IA. And we know that I is equal to never. So if we substitute the expression never for I, we'll have NEV, NEV. NEV, electron mobility for electrons, the drift velocity. To calculate the drift velocity of mobility of electron, we have Vn is equal to mobility of electron times electric field. Because the velocity of the drift velocity of electron is directly proportional to the electric field applied across the terminals of the material. For holes, the mobility becomes P. So electron, we have N. For holes, we have P. Some applications. The application of semiconductors. Semiconductors are used in almost all electronic devices. Temperature sensor, 3D printing machine, microchips, self-driving cars, calculators, solar plates, computers, electronic devices, transistor, MOSFET, used as switch in electric circuit, and many more. So here we have an example. If the mobilities of electrons and holes are 0.4 meters square per volume per second, and voltage per second, and 0.2 meters square per voltage per second, respectively. Find the resistivity of an intrinsic semiconductor with an intrinsic concentration of 2.5 times 10 raised to 19 per meter cube. Per meter cube. So this has to do with combination of, remember in an intrinsic semiconductor, we have equal amount of electrons and holes as carriers. So it implies that we are going to add them together. The mobility of the electrons and holes are given respectively as that. So we are going to find the conductivity. And then conductivity is inversely proportional to resistivity. So once we are able to get the conductivity, we should be able to find the resistivity by taking the reciprocal of the conductivity. So here we have the formula: conductivity is equal to Q, which is electric charge. Then we have the mobility, the number of electrons, and mobility of electron plus number of holes times mobility of holes. So this is the formula for conductivity. When we substitute all these parameters and get our mobility, then the next step will be to find the reciprocal of mobility. So the mobility of electron is given to us as 0.4, mobility of hole 0.2, then the intrinsic concentration is 2.5. Remember I said it before now, that holes and electrons are equal in an intrinsic semiconductor. The number of holes is equal to the number of electrons. So that is given to us as 2.5 times 10 to 19 per meter cube. And the charge, electron charge, is 1.6 times 10 to minus 19 coulomb. So if we substitute those parameters and solve for the conductivity, that gives us 2.4 per ohm per meter as the answer. That is conductivity. So if we take the reciprocal of the conductivity, we get our resistivity as 1 over 2.4, and that is 0.42 ohm meter. 0.42 ohm meter. Some industrial uses of semiconductor, we've mentioned some of them: microchips, transistor, LED, solar cell. Space vehicles, trains, and robots. Then we have importance of semiconductors. They are highly portable due to the smaller size. They require less input power. They are shockproof. They have a long lifespan. They are noise-free while operating. So these importance of semiconductor are the advantages over vacuum tube. Vacuum tube too can function as semiconductor, but because they are large, consume much power, and generate much heat, those are major disadvantages. So semiconductors have come to replace vacuum tubes. So PN junctions. When a P-type and N-type semiconductors are brought together, are joined together, they form what is called a PN junction diode. A PN junction diode. I may not really go in depth because the next lecturer will still take part of this and really go deep. So if I go in
Sir,
depth,
the slide is too enlarged, like your screen is too enlarged, so we can't see all the slides or the screen.
Guys, from your phone. Your phone
is
is not
that
from
fine?
Yeah, I know they disturb
Shrink
our
I
Shrink
think
your
it's from
stuff,
your
shrink
phone.
it.
We can see it.
phone, man.
It's better.
Shrink your stuff, shrink it.
So it's very
Yes,
better.
sir.
Okay, it's better now. So
Nice man, it's a nice man.
when a P-type and N-type semiconductor materials are joined together, they form what is called a PN junction. So here at this junction, there is what we call recombination of charge carriers. Recombination of charge carriers. P-type being that it has majority of holes, and N-type has majority of electrons. Some of the electrons in the N-type will begin to migrate and fill in the holes in the P-type. So between a boundary, you'll see that they will begin to form a depletion layer. A depletion layer. So that depletion layer will keep expanding, because once an electron fills a hole, it becomes ionized, immobile. So it will remain there. So the more holes that are occupied by free electrons, the more the width, the depletion width expands. At a point, more electrons from the N-type are not allowed to cross the depletion region, that is the junction, to go and fill empty holes. So at that point, we will require, so this is what I was saying. So here we see holes, P-type, majority of holes, N-type, majority of electrons. So at the junction here, you see them, electrons crossing to fill holes at the P-type. So while they are doing that, they are forming a depletion region, immobile region. So this depletion region will keep expanding until it gets to a level where more electrons from the N-type cannot cross to the P-type to recombine again. To recombine again. So when that happens, then if we want more electrons to recombine, it implies that we are going to apply voltage across both sides. And that is application of voltage is what we call biasing. Biasing. So when we apply voltage, the voltage will tend to decrease the depletion region as well as enhance more electrons to cross the depletion region to go and fill more holes. Now, we have two major semiconductors. One is silicon, one is germanium. For the depletion region, germanium has a potential difference of 0.3 volt, while silicon is 0.7 volts, which means that whatever battery or bias or voltage I'm applying across the junction must be for germanium must be greater than 3 volts. And if it's silicon, it must be greater than 0.7 volts. If it's less than these two values, there is no way the barrier can be overcome. And as such, it will remain like that. No extra recombination will take place. So the process of recombination and process of application of voltage is what is referred to as biasing. So for biasing, we have two types. We have forward biasing and we have reverse biasing. For forward biasing, an external voltage is added of the same polarity to the barrier potential, which causes an increase in the width of the radar, which causes a decrease in the width of the depletion region, not increase, decrease in the width of the depletion region. Is reverse bias that increases the width of the depletion region. So look at this now. Here we are forward biased. Forward bias means the terminal and the terminal of the battery is the same as the terminal of the semiconductor material. So for P is positive. P is positive, majority carrier holes is stand positive. N is negative, majority carriers electrons. So if you look at the battery, the positive terminal is connected to P and the negative terminal is connected to N. So this is called forward biasing. Now what this does is that P is positive, the cell here, the battery terminal is positive. So which means that there will be repulsion like charges repel. So that principle will come into play. Like charges repels. So there will be repulsion. The positive battery will force the holes to move towards the junction. So that is why you see all the holes have moved very close to the junction. In previous slide, you see the holes scattered all over. But here, after the forward biasing, all the holes have moved close to the potential and to the depletion region. Similarly, the electrons here on the other side is also pushed back by force of repulsion, and they are all beside the bar, that is the junction. So with this, electrons can continue to recombine with holes. So that is what positive forward biasing does. So in that process, current will begin to flow across the junction. You read the rest, I've explained it. So for reverse biasing, now for reverse biasing, you see that negative is connected to the positive and positive is connected to the negative terminal. So what happens here is unlike charges attracts. Unlike charges attracts. So here, you see the negative terminal is pulling the positive holes. So that is why they are moving away from the junction. The positive terminal of the battery is pulling the electrons away. So the depletion region, there are no charge carriers here. So what this does is that the depletion region will begin to widen up, will begin to increase. So when that happens, carriers are not able to migrate from one part to the other part to recombine. That is what reverse bias does. So all these are things that I've explained. You go through them, they are all almost saying the same thing. So the diode characteristics curve. The diode characteristics curve is a plot of current against voltage. A plot of current against voltage. Here, the forward and reverse current voltage characteristics of the diode are generally compared on a single characteristic curve. The figure, that is previous figure, depicts under the section. Forward characteristics shows that forward voltage and reverse voltage are usually plotted on the horizontal line. Forward voltage, this is the forward voltage. Reverse are plotted on the horizontal line, while the forward current is plotted on the vertical axis, that is y-axis. The point of beginning of the zero value is at the center of the graph. A forward current lengthens above the horizontal axis and the reverse current extend downward. So this graph is just telling us what is happening in that device, in the forward and reverse section of the semiconductor device. Now the reverse side has a high impedance, that is high resistance, while the forward side has a very low distance. So which means that if the resistance is low, When I increase the voltage, if you look at it, when I increase the voltage, the forward voltage, the current will be increasing. So if you look at this diagram, at a point from the origin down to some point here, it obeys Ohm's law. Ohm's law. Then after some time, Ohm's law is no longer valid. But the reverse side does not obey Ohm's law, because the reverse side behaves basically as a resistance. The reverse side is blocked. It has high resistance. So it means that current, when there is high resistance, the rate at which the current will flow will be minimal. If at all, it will flow to be very small. Diode specifications, we have maximum forward current, maximum reverse voltage, reverse breakdown voltage, maximum forward surge current, maximum reverse current, forward voltage, power dissipation, reverse recovery time. These are some specifications of diode. They are all properly defined here. And some important terms: breakdown voltage. It is the minimum reverse voltage at which the PN junction breaks down with sudden rise in reverse current. Now, what I want to explain to you now is that when we reverse bias a junction, remember that we have majority and minority carrier in N-type and in P-type. So when most of this biasing is targeted towards the majority carrier. So if I forward bias, let me look at this. Okay, let me just use this to explain. If I forward bias, this cannot go. I need a circuit that has two of them. Fortunately, it's not here. Okay. Okay, let me use this. Now, this is okay, let me just use it to explain. We'll still get to this point. Now, if you look at this circuit, this is a transistor, two PNP junction diode joined together to form NPN. So at the left side, you have a forward bias. At the right side, you have a reverse bias. A reverse bias. Because this is N-type, this is positive, so they are opposite polarities, which means that unlike charges will attract, the positive terminal will pull electrons to itself. Whereas here on the left side, N-type and negative, they are opposite. I mean, they are the same polarity. So there will be repulsion. The electrons will be pushed away towards the junction. Now, at this reverse junction between the P and N, as the VCB is increased, the width of the PN junction, that is the depletion region between the P and N here, will keep widening, will be increasing. So the more it increases, the more it prevents current from moving. However, because this is reverse bias, but if you look closely to it, you will see that there are holes in this N-type that serves as minority carriers. There are holes in that P-type, in the N-type, that are minority carriers. The electrons in N-type are majority carriers. The biasing we have put here is to block majority carriers from crossing to the P side. Now, since there are holes in this N-type, and this is positive, so the holes will see the positive terminal as like charge operates. So this positive terminal, as you can see, this positive terminal will push the holes towards the junction. While it's attracting electron to itself, it is repelling holes to the junction. And when the holes get to the junction, the minority carrier electrons in P-type will recombine with the holes that have come to line up at this junction. Let me use this into. So what I'm saying is there are holes here, few holes. They are the minority carriers in this N-type. In P-type, we have electrons that are minority carriers, while holes are majority carriers. So this positive terminal, while it is pulling electron to itself by attraction, will repel holes towards this junction. So when it repels the holes towards the junction, the minority carrier electrons in this P-type will now recombine with them. So this is also current flowing, but this current is called leakage current. Leakage current. So back to this slide. So when we keep expanding the width of that reverse bias junction, a point is reached, then suddenly that junction will break. The junction will break. And when that happens, reverse current will rise speedily and begin to move to the base back to emitter. That is breakdown voltage. We also have a knee voltage. It is the forward voltage at which current through the junction starts to increase rapidly. So that you'll see here, let me explain again. So at this junction, assuming that this is not applied and this is not applied, we are going to have a width here, potential barrier here, potential barrier that is wide. So the application of this forward bias will collapse this junction. Now, but before that happens, like I said before, for germanium, we have 0.3 volts. Who is that? For silicon, we have for silicon, we have 0.7 volts. So when I apply biasing, when I bias the junction, when I apply voltage to this input section, the voltage will increase from 0, it will be increasing upward to, if it is germanium, above 3.5, I mean above 0.3 volts before charges will begin to flow across. If it is silicon, it will go above 0.7 before charges will begin to flow across. So the voltage at which this happens is what we call knee voltage. Then we also have the peak inverse voltage. We have the maximum forward rating, maximum power rating. They are all defined there. So the working principle of PN junction, I've talked about NPN. PN junction is, PNP is similar to NPN. The only thing is you interchange the polarity. For PNP, majority charge carriers here in the emitter side is holes. Minority is electrons. At the base, you have majority electron, minority holes. At the collector section, you have majority holes, minority electrons. So the current that flows through here, that is the input section. The current that is flowing in is IE. So IE gets into the base, part of the IE form IB, and then the remaining crosses to the collector to form IC. So that gives us, by KCL, IE is equal to IB plus IC plus IC. So that is the current relationship between the emitter, the base, and the collector. The left side is the emitter, the center is the base. Yes, this is the emitter, this is the base, and this is the collector. This is the collector. So operation, the working principle, I've explained that a bit. Like I said, I don't want to go in depth so that I don't end up doing another person's aspect. So transistor operating mode, we have 3 types of operating mode. We have the active mode, the saturation mode, and the cutoff mode. The active mode, saturation mode, and the cutoff mode. The active mode is when the base emitter junction is forward biased, and then the collector base junction is reverse biased. That is the active mode. Now, one of the application of a transistor is to amplify signal. To amplify signal. So if I want to amplify signal, the transistor must be in active mode. If the transistor is not in active mode, it cannot amplify signal. So for any transistor to be used for amplification, it must be in active mode. The emitter base junction is forward. The collector base junction is reverse bias. Then the second mode of operation is the saturation mode. In saturation mode, both junctions are forward biased. So when both junctions are forward biased, it means that they are both conducting. So in this mode, the transistor is considered as a switch, switch that is on, that is ON, on switch. In this mode, that is saturation mode. And for cutoff mode, which is the third mode of operation, the both junctions are reverse bias. When both junctions are reverse bias, it means that current is not flowing, and that is referred to as off mode. Off mode. So a transistor can be used as a switch or as an amplifier. When it is used as a switch, it implies that you are going to set up your transistor in saturation and cutoff mode. So when it is at the saturation mode, the switch is off. When it is at the cutoff mode, the switch is off. When it's at the saturation mode, the switch is on. When it's at the cutoff mode, the switch is off. So connections of transistors. We have three basic configurations of transistor, which are the common base, the common emitter, and the common collector. And the common simply there is to let you know that the base is common to both sides. For common emitter, it implies that the emitter is common to both sides. And then for common collector, the collector is common to both sides. Favor Friday, what is your question?
Sorry, sir. Sir, half of your screen is cut off, sir.
Cut off?
No,
Yes, sir.
Favor, that's your
It's your
Favor,
phone.
that's it. It's your
Sir, it's
phone.
from his
I think you zoomed in. Try to zoom out.
Is your phone, Favor?
Thank you. Let me
Is
try.
your phone, Favor?
So when we have a common base configuration, the base is common to emitter and collector. So the base is like at the center, is grounded, and it's at the center. It is common to the input, and then common to the, it is both at the input. It plays a role at the input and at the output. Remember that our forward bias and reverse bias is always between two junctions, two terminals, base collector, base emitter, or collector emitter, base emitter. So two terminals at the same time. The terminals are the base, emitter, and collector. So when it is a common base, it means that the base is between the collector and the emitter. So let's look at the common base configuration here. The base is grounded. The input signal is fed between the emitter and the base, while the output signal is taken between the collector and the base. So the base is in between the emitter and the collector. That is a common base. And for a common base, the input current is E, while the output current is C. So current amplification is always output over input current over input current. So that gives us this at constant VCB. So here we have current amplification IC over IE, and its practical value of the current amplification is less than 1. That is around 0.9 to 0.999, but not exactly 1. In some cases, you can get a 1. In some cases, you can get a 1. If you have a 1, it means that IE is equal to IC. But it's very rare to get a 1. Very rare, because when look at this, when electrons or charge carriers move from emitter passing through the base has majority charge carriers. For instance, when electrons are moving from N, that's NPN, semiconductor, NPN, and electrons are moving from N, it will go through the P to the other N. So in the P, we have holes. So when the electrons enter the P, some of the electrons will fill in will recombine with holes in the P type. However, in fabrication, it's ensured that the base is lightly doped so that the electrons or the charge carriers from the emitter coming to the collector through the base are not absorbed by the holes. So that is why IE cannot be equal to IC. IE cannot be equal to IC because some of the charge carriers are used up by the base, very few of them. So that is why you have the amplification less than unity. So this is expression of collector current and emitter. E is equal to, by KCL, that is current law, IE is equal to IC plus IB. IC plus IB. Now, IC is equal to, from here we have that, if you look at this expression, it simply means that IC from this expression, IC is equal to alpha IE. Alpha IE. This is the current and the amplification that is coming from the emitter section. Now, the total current that is at the collector part is plus the leakage current. Remember, I explained to you that when we reverse bias the output side, the minority carriers will see the reverse bias as a forward bias. When we reverse bias, it is majority carriers that we are blocking from going back. But the minority carriers will see that reverse bias as a forward bias. So the holes will migrate towards the junction, and the electron from the other terminal, the base, will feed in the holes. So that we call leakage current. Leakage current. So the leakage current is here now. So the total current is this. For IC is this. We have seen this before, but this, which is the leakage current that I explained to you before now. So we can play around with those formulas and then have that expression. You lay your hands on it and just practice it. Practice it and you have that. Remember that everything we have in this bracket is IE. Remember that IE is equal to IB plus IC. So if we replace IE with this in the bracket, we have that expression. So the next thing to do there is to simplify. Open the bracket, take common terms, and then simplify to get that expression. So this is input characteristics.
So what's that ICBO?
ICBO, I explained it before. That is the leakage current.
Okay, okay, sir.
Do you remember my explanation for leakage current?
Yes, sir.
Okay, that is the leakage current. So this is input characteristics. This is output characteristics. And then input resistance, output resistance. For common emitter configuration, the amplification. This is common emitter configuration. Common emitter, the emitter is grounded here. The emitter is grounded. So the emitter and the base is base form the input signal, while the emitter and the collector form the output signal. So the output current this time is IC, the input current is IB. So output current over input current will give you current amplification. That's what we have. So this time the current amplification is greater than 20. It ranges from 20 to 500. So the same way you can play around with this formula and get a relationship between beta and alpha. Then the input configuration and output configuration. The last one is the common collector configuration. So if you look at the transistor diagram, you see the emitter is pointing up. The collector is pointing down, grounded. So this time, the base and the collector form the input, while the emitter and the collector forms the output. So the same way you find their current amplification, the input is IB, the output current is IE. So current amplification becomes IE over IB, and that is gamma. So the same way we did for the other one, you solve and find a relationship between the three of them. So this is a comparison between the three types of connection. Here is an example. In a common base collector, emitter current is that, collector current is that, calculate the value of the base current. So you subtract the collector current from the base current. Here is another example, and here is another example. Friday, what is your question?
Sorry, sir. Sir, please, can you explain the graph for the common emitter, common base, and common collector? The graphs you showed.
These graphs,
Yes, sir. Yes, sir.
okay. Let me just take one. The graphs are almost the same, but let me take one. So if you look at this graph, it's just like experimental results. Now, this side is the input, IN. This is the output side. So if I keep this voltage, VCB, constant and vary VEB or VEE, I keep varying this. Let's say I start with 1 volt, then the next is 2 volts, the next is 3 volts, the next is 4 volts, and let's say I take up to 10 volts. So when it's 1 volt, IE will change. I will give me a value, and the value I'll get for IC will be known. Then if I replace 1 volt with 2 volts, I'll get another value for IE. I'll get another value for IC. If I replace the 2 volts with 3 volts, I'll get another value for IE. I'll get another value for IC. On and on. Why are you raising your hand? You ask question, I'm explaining, you are raising your hand again. On
No,
and
my
on.
phone was pressing by itself, sir.
So VCB is kept constant. Let's say the VCB is 2 volts. So I have VEE running from 1 to 10 volts. So definitely I'm going to have different values of IE and IC. So that is chapter 1. Chapter 2, I will move VCB, let's say 3 volts, and leave it at 3 volts, constant, while I repeat the same process. That is from 1 volt to 10 volts. I change VEE from 1 volt to 10 volts. I will definitely have different IE and different IC that is completely different from when VCB is 2 volts. So now I have 2 sets of reading. This again, I move to make VCB 4 and leave it constant while I vary VEE from 1 to 10. I will have different set of IE, different set of IC. So if I now plot my graph of IE against VEE, that is my input characteristics. So that will give me this kind of graph. So if you look, you will see that I have three graphs. When VCB is 1 volt, when VCB is 10 volts, and when VCB is 20 volts. So I have different values of IE and different values of VEE. So that will give me 3 different graphs. If I move again to make, that is, move up again to make this like 40, so I will have 4 graphs here. But here now, you see we have 1 volt, 10 volt, and 20 volt. So it means that VCB was kept constant at a time for 1 volt, then later kept constant for 10 volts, and later kept constant for 20 volts. While VEE or VBE is changing from 1 to 10, I will have different values of IE and IC. So this is input characteristics. Output characteristics here. So this is input characteristics. That is what you use to plot this graph. You see there, VBE against IE characteristics is called input characteristics. IE increases rapidly with VBE. It means input resistance is very small. That is forward bias because it's input resistance is small because it's forward bias. While VCB is kept constant. So here you get your input characteristics. For output characteristics, you keep IE constant this time. You keep IE constant and very VCB. So if I keep this current, IE constant, and vary this, say from 1 to 10 volts, I will have different values of IC. So if I plot a graph of IC against VCB, that will give me output characteristics curve. So that is what you have here. That is what you have here. Plot VBC or VCB against IC. IC varies linearly. Then IE is kept constant. So when IE is 0, of course, when IE is 0, there will be no current in the circuit because it's IE that supplies current to IC. What's your question, Morakinyo Joshua? Why did you raise your hand and you are not in the class?
Yes, I don't worry, sir. I've comprehended. Thank you, sir.
Okay. So, for Friday, is that okay?
Sir. Yes, sir.
All right. So, that is the end of our class. You write your test by next year before the exam, because I know you are not going to do online exam. So before your exam, you write your test. You are not going to even do online tests. So by next week, Dr. Lukman will take over the class.
Sorry, sir. Sir.
Yes.
Sir, please, can we get the syllabus for this course, like the scheme?
You don't have student handbook?
Yes, sir.
You don't have?
Sir, the one that we have, it doesn't seem to contain some of the things you are taking, like the transistor is not there. It's not in the handbook.
Who says so? The semiconductor not there? Is semiconductor not there?
They give to us.
Is semiconductor not there?
It is there, sir.
Transistor is a semiconductor now.
Okay, because what they only wrote for semiconductor diodes and PN junctions.
Okay, so now you have little knowledge above what is expected of you. And
Okay,
that
sir.
is
Thank
not
you, sir.
all. Like I said, because I've already moved into another person's part. That is why I'm not going deeper. I'm just scratching the surface for you. So she will continue. All right. So I've sent the YouTube link to one of you. So forward it to the platform so that anyone that wants to go back to listen to the lecture can always, and those who did not, we are not able to join the class, can always go back and listen to the recorded version.
Okay, sir.
All right.
Thank you.
Send your names, everybody, your name, matric number, and department for record
Okay,
purpose.
sir.
Yes, send it as chat.
Good evening, sir. Please, do we know what format the exam will be in? Theory or OBJ and theory, or
Not
just
theory.
OBJ?
It's OBJ.
Okay, sir. Thank you, sir.
All right.
I got the slide.
Is that what?
I said, can we get the slide?
The slide. Okay, I'll think about it. But pray
Please,
very
thank you,
hard.
sir.
So that when I'm thinking about it, I'll think positive.
Okay, sir. In Jesus' name, God will make you think positive, sir.
Sir, please help us to think positive.
Please, sir. You will enjoy your Christmas and New Year, sir.
Amen.
All right.
Thank you so much, sir.
We love you, sir.
We love you. You will never.
Oh, madam, it has.
Stop, please, this slide. Stop, please, this slide, sir. Stop, please.
He said he's going to send it. That we should pay.
We should pay.
We should
Pay.
pray. Pray.
Okay. In the name. Oh. Bismillah.
Morak.
Pastor Debinke, let's pray.
You didn't mention my name for class, Joe. Eh?
Adebinke, yeah, let's pray.
In Jesus' name.
I don't do any fellowship here.
In the mighty name of Jesus. Lord of in the
So
mighty
the
name
time we
of
not finish
Jesus.
Friday in online class.
Father Lord, we put the mind of Dr. Humphrey in your hands. Father, may he think positive in Jesus' name. He must send the slide to us in Jesus' name.
May all of you on the call not blowing.
What do you say? Professor is online, no?
What are you doing there? You have finished your exam? Eh? Oh, thank you. Please, I'm through with them. I'm through with 200 and 300 level class.